All right, I wanted to make sure that we got the problem to the third page. So we're doing things a little bit differently here. So we have this roller coaster. It's got a height of 200 meters, and we want to use conservation of energy to get the speed of the roller coaster halfway up the loop. So it's actually making it only to here. So let's be clear that the height here is equal to the radius. Now, to get that speed, we're going to start off with gravitational energy equal to mgh, and it's going to make it up to here where it's going to have a combination of gravitational energy and kinetic because it is moving. And let's be clear that this h is in fact the radius, and that's what we're going to have here. So there we go. Now, setting these equal, we're going to have mgh equal to 1/2 mv squared plus mgh right here. Let's cancel some masses as we can actually do that. And I'm sorry, this here is mgr at the very end. So we've got 10 times 200 equals our unknown v squared over 2 plus 10 times this radius, which is just 20. So we got a little bit of rearrangement to do, so we're going to end up getting 1800 equals v squared over 2. And so we're going to get 3600 equals v squared. And when we isolate that, v is going to end up being 60 meters per second. All right. So that is question number 9. And we're going to continue with question number 10. We want to know the normal force on the roller coaster. So even though the normal force points this way and gravity points down, the normal force is in fact the only thing generating a circular force because it's the one force that goes towards the center of the circle. So it actually turns out in this case, Fn is mv squared over r. And given that we've studied that the circular centripetal force has to point towards the center, I would consider this kind of a question fair game because it does test your knowledge of circular forces. So it's not just enough to know to solve the very problem that I put in front of you, but the ability to take the material that we've studied and apply it to slightly different but related situations. So in this case, the normal force is going to end up being 200, and v squared is going to be 3600. It's going to be 3600 divided by our radius, which is 20. So here we're going to end up getting 72,000 newtons worth of force. Now we want to know what is the speed of the car at the top of the loop if the normal force on the car is twice its weight. So let's be clear. At the top of the loop, we're going to have Fn and Fg. So this means that Fn and Fg at the top of the loop, so now we're dealing with here. For number 11, we're right here. Okay. So Fn plus Fg, and the effect is that we move in a circle. So Fn is 2mg, so we have 2mg plus mg equals mv squared divided by r. And so I can actually cancel the m's all across here. So I'm going to end up getting 3g equals v squared over r. Now g is 10, so that's 30 equals v squared divided by 20. V is going to be the square root of 600. And when I actually solve that particular problem, we're going to end up getting 24.5 meters per second. All right, now it says how high does the hill need to be for the car to make it up the loop at the speed we figured out in 11. So here's the idea. That hill is mgh, and the effect is that we're going to get kinetic energy, and at the top of the loop, our height is 2 times r. So just to kind of be clear, we've got h here, and the height here is 2r. And we have a speed. So what's nice is the m's actually cancel across here too. Now I know that v squared is 600 from up here, so I can say 10 times h equals 1/2 times v squared, which is 600. I'm getting that from here, plus 10 times 40. So working with this, I've got 10 times h is 300 plus 400. And so h is going to end up being 70 meters high. So that's it for page 3.